Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD heat transfer analysis, parametric study and optimization of a shell plate heat exchanger using SolidWorks 2022. This is the model. You can see these are the plates which is made up of copper, and these plates are inserted inside a hollow shell. The shell is made up of stainless steel. To understand the geometry, let us have a segmented view of this model, and we can cut it from specific planes. Let us cut the model from right plane. You can see this is the sectional view of this shell plate heat exchanger, and from bottom side we'll pass water at a temperature of 20 degrees centigrade. It will flow in the forward direction. While flowing water in the forward direction, it will pass in the left hand side and right hand side direction depending on the structures of the bones. Ultimately it will go up, right? So the thing is, from here will flow water at a temperature of 20 degrees centigrade. It will flow in the forward direction. By the same time, it will flow both right hand side and left hand side direction, and ultimately it will come from this top exit. And from the top opening here, we will provide water at a higher temperature. This one will be surrounding these plates. There will not be direct mixing of hot and cold water, and inside these plates, cold water will be warmed up by way of convection. Okay, let us view inside of the shell. For that, we can make this plate transparent. The plates are completely transparent right now. Now we can view the flow path in a better way. So the thing is, from this bottom opening, we'll provide cold water at a temperature of 20 degrees centigrade. It will flow in the forward direction. By the same time, it will flow both left hand side and right hand side following these bone type of structures, and ultimately it will come out from this top exit. Series of plates are inserted, and these series of plates are welded together to make this one as a compact model. And outside these plates, we are providing hot water at a temperature of 100 degrees centigrade. It will flow from the top entry and it will come out from the bottom exit, right? So without wasting time, let us start our simulation. And for starting the flow simulation, we need to start from here. We know that for starting a flow simulation, we need to have a closed environment. That is, we need to provide some kind of leads. Leads are already provided. Actually, the back side of this plate and this shell is completely closed. This is the entry of cold water, and this is the exit of cold water. At the both entry and exit, we have provided some kind of leads. Similarly, this is the entry of hot water, and this is the exit of hot water. Both the entry and exit of hot water also have provided some kind of leads. So this is completely closed volume. And for starting this flow simulation, we need to create flow simulation environment, and that will be created with wizard itself. So default name of the project is project 2, because already we have done one project. That is first project we have already done. So we're keeping the name of the project as project 2. Next to that, we need to select unit systems, and we're considering SI system, and from parameters we're considering temperature to be in degrees Celsius. Next to that, analysis type, it will be internal analysis, and from physical features we need to select fluid flow with conduction, and gravity will be involved, and the direction of gravity will be Y as indicated by green arrow in the upward direction. So along Y it will be minus 9.81 meter per second square, and along Z it will be 0. Done. Next to that, we need to select fluids, and we're considering only one fluid, that is water. Water at different temperatures will be passing from different locations. So our fluid is water. And next to that, we need to select solids. Two different solids we are considering in this case. The plates are made up of copper, and the shell is made up of stainless steel 321. So at this moment, we will consider copper only from metals, and the remaining materials will be provided during application of boundary conditions. So from metals, we are considering copper. Next to that, we are considering default outer wall thermal conditions and roughness. And finally, thermodynamic parameters. Pressure will be 101.325 Pascal, and temperature will be 20 degrees centigrade. and solid parameters also it will be 20 degrees centigrade. Let us finish this. You can see this is the computational domain. Fluid volume is being generated. Now this is the computational domain. We can hide this domain at this moment, and we can apply our required fluid subdomains. And for selecting different fluid subdomains, we can have a segmented view of this model. So we'll cut it from right plane, grain check, and we need to provide different fluid subdomains. Let us rotate this one a little bit. Fine. Now fluid subdomains, insert fluid subdomain, and we'll provide cold water from this one at a temperature of 20 degrees centigrade. So lead 5 is selected. From this one we have to provide cold water at a temperature of 20 degrees centigrade, and from thermodynamic parameters we need to provide those conditions. You can see thermodynamic temperature is 20 degrees centigrade and pressure is 101.325 Pascal. So this is the fluid subdomain for cold water at a temperature of 20 degrees centigrade. From this opening we are providing cold water at a temperature of 20 degrees centigrade. This is the fluid subdomain for cold water, right? Grain check. Next to that we need to provide fluid subdomain for hot water at a temperature of 100 degrees centigrade. That will be passing from this one. So another fluid subdomain is needed. Insert fluid subdomain, and it will be water at a temperature of 100 degrees centigrade, and it will pass from this top opening. This is the fluid subdomain of hot water. We can see here the volume of hot water is much more than that of cold water. Okay, great check. Next to that we need to select different materials. Insert solid materials, and first of all we'll select copper for the plates. So predefined it will be metals, and from metals it will select copper. And for selecting the copper plates we can select it from the geometry itself, that is solid geometry. We can select copper plates from here. Let us select the first one. We'll select shift and select the last one. You can see here all the plates are selected from the solid geometry, and it is made up of copper. Grain check. Next to that we need to select the shell, which is made up of alloy steel. So solid materials again, insert solid materials, and we need to select the shell and also the different lids. Let us select the shell and the lids, which is made up of alloy steel, right? So it will be predefined alloys, and it will be stainless steel 321. Shell and the lids are selected. It is made up of stainless steel 321. Grain check. So all the materials are defined. Next to that we need to apply our boundary conditions, and that can be done from here itself. Insert boundary condition, and from bottom entry we'll provide cold water at a temperature of 20 degrees centigrade at a very low velocity. Let us provide inlet velocity of cold water as 0.01 meter per second, and definitely its temperature will be 20 degrees centigrade. That can be viewed from thermodynamic parameters. Let us select the location. Selected. Grain check. First boundary condition is applied. The second one to be applied, insert boundary condition. It will be hot water at a temperature of 100 degrees centigrade from this opening, right? Selected, and velocity of this one will be 0.001 meter per second. And we can see thermodynamic parameters, it will be 100 degrees centigrade. Grain check. Both the boundary conditions are applied. Next to that we need to apply boundary conditions at the exit. That will be atmospheric pressure at the exit locations. So boundary conditions, insert boundary condition. It will be environmental pressure at the exit of these plates. Grain check. It is done. And the last one, that is the exit of hot water. Let us rotate the model a little bit. Boundary conditions, insert boundary condition. It will be environmental pressure at the exit of hot water. Selected. Grain check. All the boundary conditions are applied. Now we can do one thing. We can rename these things. The first one, the inlet velocity of water, we can rename this one as inlet velocity of cold water. Similarly, second one will be inlet velocity of hot water. Done. And the environmental conditions, we can rename this one as environmental pressure at cold water exit. And the last one, that is environmental pressure at the hot water exit. All the boundary conditions are applied. Next to that, we need to select some goals. In this case, we are considering 3 different goals, and initially we want to have 2 service goals, that is the temperature of fluid at the exit locations. By the same time, we want to have some kind of equation goal, that will be the effectiveness of this heat exchanger. We want to find out LMTD, or logarithmic mean temperature difference of this shell plate heat exchanger, right? That will be an equation goal. So first of all, we need to find out some surface goals. Insert surface goals, and we need to have average temperature of fluid at the exit of plate and also the shell. We can select these things. Let us select those locations. This is the exit of cold water at lid number 6, selected, and we need to select the down one, and this is the exit of hot water, that is lid number 4. We have selected phase 1 and phase 2, and we want to create goals for each of them separately, and the goals will be average temperature of water at different phases, green check, and we can rename this one as, first one is average temperature of cold water at exit. First one is done. Second one also, it will be average temperature of hot water at exit. So 2 surface goals we have defined. Next to that, you need to find out that equation goal, that is the logarithmic mean temperature difference of this heat exchanger. So insert equation goal, and for initiating this equation goal, first of all, we need to start with brackets, and we can have the required parameters from the boundary conditions and from goals. First of all, we will select the boundary conditions, that is the temperature difference of different entry locations. Boundary conditions, it will be the difference of hot water minus cold water at entry locations, right? So we can select it from here itself. Inlet velocity of hot water, that is temperature at the inlet location, is 100 degrees centigrade, minus, we need to select inlet temperature of cold water from here, it is 20 degrees centigrade, bracket closed, minus, again bracket started, and we can do one thing. At the starting level, you can put another bracket. Now here itself it will be the difference in temperature at the exit locations, and that will be obtained from the goals. So we are adding goals from here. It is the difference of average temperature of hot water and average temperature of cold water. So it will be first one, average temperature of hot water at exit, minus average temperature of cold water at exit, bracket closed, minus, you see here we have provided 3 buckets, right? So another bracket should be provided here, divided by ln. Now we can copy the whole things what we have written right now, copy, and that can be pasted after ln, Control V, and we can change this one. It will be, instead of minus, it will be division. So we can check it, that LMTD is the difference in temperature of hot water and cold water at the entry level, minus difference in temperature of hot water and cold water at the exit level, divided by ln of difference in temperature of hot water and cold water at the entry level, divided by difference in temperature at the exit of hot water and cold water, right? So we can accept this one with green check and rename this one as LMTD. This is known as effectiveness of heat exchanger. So all the goals are defined. Next to that, we need to run this. We have already run this one in project number 1, so we can see the results from here itself. Project 1. We'll go back to project 1 and see the results. Okay, so with same data we perform this simulation. Now results are not loaded. We need to load this one. Let us load the results. So results are loaded. Now first thing what we'll do is, for viewing the dynamics of flow particles and different cut powers of pressure and temperature, we need to make the model completely transparent. We can make the model completely transparent from here. The model is little bit transparent right now. You can rotate a little bit. Now from this front plane and side plane, you can see the different cut plots of pressure, temperature, and also the dynamics of flow particles, right? So for seeing this one, we need to start from cut plots. Insert cut plots, and first of all, we want to see temperature distribution, temperature of fluid through these plates. Instead of pressure, we can change it to temperature of fluid, and it will be viewed from front plane. Green check. You can see this one. It will be better to see this cut plot in the form of an animation. Let us play. You can see here, downside temperature of water is blue, which is in the range of 28 to 45 degrees centigrade, and top side, the temperature of exit of cold water, it is high, and the color of this one is showing it is in the high range. And through the shell, temperature of water is very high, it is in the range of 91 to 100 degrees centigrade, and through the plates, temperature is lying in the range of 20 to 45 degrees centigrade. Now we'll see these things from sidewise. So let us clear and hide cut plot 1, edit definition, and we want to see these things from right plane. It is done. Now we can see from right side, and for that you need to change the orientation of this heat exchanger. We can see it from right side, and it will be better to see this in the form of an animation. Let us play. Actually, the plates are not completely transparent, that's why you cannot see what is going on inside the plates. You can see outside these plates through the shell only. Next one, we can see surface plots, but it is not useful because we have already seen that at the boundary or at the surface, temperature is in the range of 98 to 100 degrees centigrade. So instead of surface plots, next one we will go for flow trajectories. That means we want to see dynamics of flow particles through this shell plate heat exchanger, right? It is better to have a segmented view of this model. Then we can select the locations in a better way. So we can cut it from right plane, and so flow trajectories, insert flow trajectories, and instead of 20 numbers of flow particles, we can make it 200 numbers. It will be initiated from this location, entry of cold water, and you can select the other locations also, like the exit of cold water. Similarly, we can initiate from hot water entry also, and it will be moving out this hot water exit also. At the same time, we can select the inside surface of the shell. Now we can generate this particle study. It is going on. It will take some time for generating these particle studies. And these are dynamics of flow particles. You can view it in the form of an animation. Let us play. It's not clearly visible, so outside it is actually hot water, and through these plates we are having cold water. You can see one path. Cold water is passing in this way, front direction, but at the same time it is passing in a circular way also, right? And from this opening it is coming out. It is not clearly visible. You can view it from front plane also. Let us play. You can see how the particles are moving throughout this shell plate heat exchanger, right? Actually, from this one, cold water will be passing. It will go in the forward direction, but at the same time it will circulate along the path of these plates, because through the plates we are having some kind of bone type of structures. Following that path, cold water particles will be moving, and it will be warmed up by convection from hot water, right? You can view it from front plane also. So these are the dynamics of flow particles of hot water, and these are actually for cooled water inside the shell. Next to that, we want to see our goal plots. So insert goal plots, and we want to see all the goals, and we can export it to Excel. First one is LMTD. It is showing that after 281 numbers of iterations, LMTD is 67.64, and second one is average temperature of hot water at exit. Initially hot water temperature was 100 degrees centigrade. So you can see here after 281 numbers of iterations, average temperature of hot water at exit is 99.4 degrees centigrade. Next one is average temperature of cold water at exit. We can see here after 281 numbers of iterations, average temperature of cold water at exit is 42.77 degrees centigrade. That means we can see huge rises in temperature of cold water. Initially cold water temperature was 20 degrees centigrade, and at the end we can see its temperature is 42.77 degrees centigrade. That means we can see there is a gain of temperature of 22.77 degrees centigrade, right? Let us close it. Next to that, we have done one parametric study by varying different input variables. Input variables may be the temperature of cold water, or it may be the temperature of hot water. By the same time, we can vary the mass flow rate of this cold water and hot water. In this parametric study, we have varied the velocity of cold water from inlet. Let us see the parametric study from design of experiments and optimization. In this case, what we have done is we have changed the inlet velocity of cold water from 0.02 meter per second to 1 meter per second. And let us see the goals. So actually 5 set of experiments we decided to perform, but it is taking huge amount of time. So we have finished this one with 3 numbers of experiments. When the velocity of cold water entry is 0.755 meter per second, in that case average temperature of cold water at exit is 28.3 degrees centigrade, and that of hot water at exit is 97.17 degrees centigrade. In experiment number 2, when inlet velocity of cold water is 0.265 meter per second, in that case you can see average temperature of cold water at exit is 37.49 degrees centigrade, and that of hot water is 98.57 degrees centigrade. In experiment number 3, when inlet velocity of cold water is 1 meter per second, in that case you can see that average temperature of cold water at exit is 26.34 degrees centigrade, and that of hot water at exit is 98.76 degrees centigrade. So from this data, it is clearly understood that when we are increasing the inlet velocity of cold water, in that case the temperature of cold water at exit is decreasing, right? If we provide more mass flow rate of cold water, in that case the temperature at the exit of cold water will be decreased. You can see here when inlet velocity is very high, in that case temperature at the exit of cold water is very less, it is 26.34 degrees centigrade, and when inlet velocity is very less, in that case temperature at the exit of cold water is 37.49 degrees centigrade, right? Now instead of stopping it here, we can go for some kind of optimization. That means if we want to achieve some specific temperature at exit of cold water or at the exit of hot water, we can go for some kind of optimization, right? With this one, we will conclude our today's analysis. It is a very simple analysis of a shell plate heat exchanger. In this analysis, we have provided cold water from this opening and hot water from this opening, and as a goal we have found a temperature at the exit of cold water increased by approximately 27 degrees centigrade, but in case of hot water, the temperature of hot water has decreased by very little amount, approximately 2 degrees centigrade, right? So let us close it. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.